Good afternoon and welcome to today's Machine Design webcast. Our topic today is how to use Power over Ethernet in motion control applications, sponsored by Applied Motion Products. I'm Bob Avner with Endeavor's Design Engineering Group. Let's talk about how you can participate in today's presentation. First, if you have any technical difficulties during today's session, please hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. We also welcome your questions during today's event, and we'll get to as many of those as we can during the Q&A presentation that will follow. So please feel free to submit your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the Machine Design website within the next week. You'll be notified by email when the archive is available. So let's meet this afternoon's speaker. Eric Rice has worked in the motion control industry for more than 20 years, specializing in step motors, servo motors, drives, and controls. You can learn more about Eric by clicking on the blue speaker bio widget on your console toolbar. So we're ready for this afternoon's presentation. Eric, thanks for joining us, and we're looking forward to this afternoon's presentation.
Thanks, Bob, for that nice introduction. Welcome, everyone, and thank you for joining today's webinar. Today, we're talking about Power over Ethernet, or PoE, and its use with motion control devices. Now, I have a feeling that many of you have a pretty clear understanding of what PoE is, but I also have a feeling that some of you might also be wondering exactly what this presentation is about. So to kick things off, I'm going to start with a couple of slides that clarify exactly what it is I'm talking about today. The PoE that I'm talking about today is a solution for providing data and power over standard Ethernet cables, which means Cat5 and Cat6 cables. And this solution includes specifications that are standardized by the IEEE, specifically IEEE 802.3. The reason I want to emphasize this point is that what I'm not talking about today is a proprietary solution for PoE that is specific to Applied Motion Products or any other vendor. That means because this PoE standard is standards-based and readily available from a wide range of hardware vendors in the marketplace, you can feel confident that if you use it, it will be compatible with other hardware that you might choose. This next slide shows the wire colors and pin assignments of a typical RJ45 connector on a standard Ethernet cable. You don't have to worry too much about the wire colors shown here. Just understand that there are 4 twisted pairs of data lines in an Ethernet cable, and each pair is represented by a different color and its striped mating conductor. What's important for today's discussion is that the Ethernet cable and the connector have 8 pins. And you can see the pin assignment here in this first table for standard Ethernet. And the thing to note here is that only 4 of the 8 pins are used for receive plus, receive minus, transmit plus, and transmit minus. So that leaves 4 pins unused. And the first implementation of PoE, shown here in the second set of tables, is what's called Mode B. This uses those 4 unused pins for transmitting DC power. There are 2 pins for DC plus and 2 pins for DC minus. Now, there's a second mode, Mode A, where the DC plus and minus are actually shared on the receive and transmit lines. And this is perfectly okay. It's legitimate to do because the Ethernet electronics on either end of the cable can very easily ignore those DC biases on the data lines because they're just looking at the differential signal between the plus and the minus. So it's perfectly okay to do that. It's sometimes referred to as phantom power. And one thing I want you to keep in mind is that this is background information. You don't really need to remember this because whatever version or flavor or mode of power over Ethernet that your device might be using, the switch that it's connecting to will automatically figure out what mode it's using and send the power on the correct pins. So this is all transparent to you, but I wanted you to see how power is exactly transmitted over an Ethernet cable. Now, this next set of slides shows some standard Ethernet connections with a basic type of block diagram. This is a non-PoE network, so all the hardware in here is just standard Ethernet stuff. Over on the left, we've got a switch with a power supply and a few Ethernet cables coming out of it. Over on the right, we've got a device with its own power supply. And then there's a data connection between the switch and the device that's providing Ethernet communications. Now, this diagram pretty much illustrates every wired connection on the planet today. It includes your computer that's hardwired into a switch. It includes a printer. It even includes servo drives that are connected to an Ethernet network. So this is what we're all used to dealing with every day. Now, I've changed this same diagram a little bit by highlighting items that have PoE functionality in blue. So now we've got an Ethernet switch on the left with PoE ports, some blue data lines coming out of it that have power and Ethernet, and then a PoE device over on the right. And the main thing to note here is there's no power supply for the PoE device. That's like the big thing here. So now the connection between the switch and the device is data and power. And even if you're new to PoE, you're probably not as new as you think, because there are a lot of devices around us every day that use PoE. Good example is the phone in your office. If you've never looked at the back side of your phone, I encourage you to do it. There will usually be an Ethernet cable there, and sometimes there will only be an Ethernet cable there. And if there's just an Ethernet cable, no cable for a wall adapter for power, that phone is running on power over Ethernet. Another example is IP security cameras. Those are very often PoE powered, and wireless access points, which are becoming super popular in office networks and home networks. Those are very often powered over Ethernet as well. And as we'll find out in today's presentation, there are some motion control devices, i.e. motors, that are powered over Ethernet as well. Now, this next slide is just like the previous one, but the reason I put it in here is I shaded the switch a little bit differently. I shaded it partially black, partially blue. And the reason is this is more representative of a typical switch that you'll find in the marketplace. So when I survey hardware switch vendors in the marketplace that are selling industrial switches with the kind of PoE that we're interested in, most of those switches have some number of ports that are non-PoE and then some other ports that are PoE. And so I just want to bring that to your attention. Also, another very forgiving thing about PoE is that the switch that's providing power to the devices is smart enough to know not to provide power to devices that don't need it. So if you have an Ethernet switch with available PoE ports and you have a device that doesn't accept power over Ethernet, it's okay to plug it into that port anyway. The switches automatically negotiate whether a device needs power or not and provides the power if it does and does not provide power if it doesn't. So again, PoE is a very easy technology to use. Now, this slide shows a little bit of terminology relating to IEEE. So the switch in this case, which is providing the power to the device, is what's called a power source equipment, or PSE. And because it's at one end of the data connection, it's what's called an end-span PSE. The device is simply the powered device, which is receiving the power. Now, what do you do if you have a PoE device? Could be a motor, could be a sensor, it could be some other device that you really want to incorporate into your equipment or your factory floor, and you have an Ethernet switch in your control panel, but it doesn't have any PoE ports. Well, they have a solution for that too. It's called an injector. And the sole purpose of an injector is to add power into the data connection. So there will be a data-only connection coming from the switch to the injector, and then from the injector to the device, you'll have data and power. The injector doesn't do anything with the data. It just passes it back and forth. All its sole function in this circuit is simply to provide power to the device. I've got a picture here of a simple injector that we offer as an accessory. It's a single connection, so it supports just one device, although there are injectors on the market that you can find that support more than one device. And you can see in this small photo in the lower right that there's a yellow Ethernet cable coming into the injector, and then a yellow one, another one going out to the motor or the device, providing the power along with the Ethernet signal. In terms of IEEE terminology, the main difference here, the injector is now the PSE, the power source equipment, and because it's in the middle of the data connection, it's what's called a mid-span PSE. And then the powered device is, of course, still the powered device. So that gives you, hopefully, a broad view of PoE and what it is we're talking about today. As I mentioned, I think a lot of you already probably have a pretty good handle on this, but hopefully some of you feel a little bit better about what it is. One of the big takeaways that I want you to have is that PoE is really friendly to use. There's just a couple of things to keep an eye out for, which we'll explain here now. So the next question is, how much power can we get with PoE? So we know that we can connect all these devices with it. How much power can we actually use? So this slide shows the IEEE standards for power over Ethernet. And you can see in this table that there are 4 main types of PoE currently in the standard. The first one is what's referred to as type 1, or just plain old vanilla PoE. And a couple of rows I want to point out in this table are the first 2. So you can see in these first 2 rows, there are actually 2 power specifications for PoE. The first one is the power available at the powered device, and the second one, which is larger, is the maximum power delivered by the PSE. And the reason I want to call this to your attention is that there's a slight difference here, which I believe is in the spec to accommodate voltage drops across long cable runs. But from the perspective of a device manufacturer like us, we're looking at the first row. We want to know what we can do with those 13 watts. Whereas the manufacturer of a switch is probably concerned about how much power they have to be able to guarantee delivery of. So they're going to be looking at the higher number. And as a user, it's important for you to know this slight distinction when you're shopping for hardware, because you might see one device saying one number and another device saying a slightly different number, and you might otherwise think, wow, these might not be compatible. But it's important to note this difference in the specification, in the standards, and hopefully this will lead you to selecting the right hardware. Okay, so 13 watts, what can we do with that? Not a whole heck of a lot in terms of motion control. So where things get more interesting is when we get up to type 2. And this is also known as PoE+. So you won't always see the plus when you're looking at specifications for hardware. So you also want to be familiar with the spec number, or the standard number, which is 802.3AT type 2. Little technical sounding, but it's important to know that. And then and then also a lot of manufacturers will include the plus, so PoE+. But basically it means 25.5 watts at the device. And so it turns out with 25.5 watts, we can actually get full speed torque performance out of some smaller size step motors. And that's where we're going to focus the rest of today's discussion, is on this 25.5 watts for PoE+. Now, there are a couple of other types, type 3 and type 4. These primarily use what's called 4-pair PoE, or 4P PoE, where in this implementation, all 8 pins on the Ethernet cable are used for carrying power. And as I mentioned earlier, that's so totally okay, because the DC bias is easily filtered out from the data. But when we do that, when we carry power on all 8 wires, now we can get up to 51 watts or 71 watts at the device, and then we can start doing even more. So we'll come back to that in a little bit, but for now I want to focus on PoE+ and what we can do with those 25.5 watts of power. So what kind of motion control solution can we come up with for 25.5 watts of power? To answer that, I want to keep in mind 3 main features that we want to incorporate into our solution. The first is standard cabling. As I've mentioned already a couple of times, this is a standard-based implementation on IEEE 802.3, so we're going to use standard Ethernet cable, Cat5, Cat6 cable, the kind that's readily available all over the place, and we're going to support both RJ45 connectors and M12 connectors. We want to max out the torque and speed is number 2. And looking at step motor frame sizes, that means we can get full torque and speed out of NEMA 8, NEMA 11, NEMA 14. We can also get some decent torque out of NEMA 17 and 23, but we can't really get all the power out of them, so we'll leave those for later. And then minimal wiring. Now, minimal wiring is one of the main reasons that you use PoE in the first place. You're ditching an entire cable. You're also ditching an entire power supply, and that has huge benefits in a lot of applications. But we're down to one cable as well, and we certainly don't want to add a bunch of cables back in. So in terms of the motion control solution, sure, we could come up with a stepper drive that's powered over Ethernet, and then have a separate motor that we connect to that drive with a motor cable and an encoder cable. But now we've got 2 new cables we're introducing into the system. So we'd be much better off going with an integrated motor solution, where the drive is part of the package of the motor. We don't have to worry about a motor cable. We don't have to worry about an encoder cable. We just have to connect PoE to it. So what does this solution look like? Well, I mentioned standard cabling. These are photos of the back of our motor. We'll have RJ45 and M12 options. We'll go with the largest size step motor that we can max out the torque and speed, which is a NEMA 14. If you're unfamiliar with that, it means that the mounting face of the motor is 1.4 by 1.4 inches. And as it turns out, our motor is just under 5 inches long. And as I've already mentioned, minimal wiring. We're going with an integrated motor solution. So that means on the back of the step motor, we've got an encoder on the rear shaft. All the drive electronics are packaged in the rear. And then on the very back, we have our PoE connector, either RJ45 or M12, and some status LEDs. And the end result is what we call TSM14 PoE step servo integrated motor. So it's a little bit of a mouthful. I'm going to break down some of what's in here. TSM refers to an entire family of step servo integrated motors that we offer. If you are new to the term step servo, it was our trade name for closed loop steppers. So we take a traditional step motor, we put an encoder on it, and we run it with servo controlled firmware so that we can servo the current, the velocity, and the position. So basically, we run a step motor like a servo motor. It's still a fairly low-speed animal. It doesn't give us thousands of RPM of speed, but it does give us some other nice benefits, which I'll show in a second. So TSM refers to a whole family of step servo integrated motors that we offer, i.e. closed-loop stepper integrated motors. And this is the TSM14 PoE is just part of that. 14 is the NEMA 14 frame size, and PoE, of course, is power over Ethernet. So before I get into step servo benefits, I want to come back to that reduced wiring and give you an example. This slide has a theoretical 4-axis motion control system that could be mounted on a piece of equipment or a machine somewhere. And at the bottom of the screen, we've got 4 axes of stepper motion. We've got a step motor with an encoder and a stepper drive. And the yellow and gray lines there show the motor feedback and motor power connection between the drive and the motor. And then all the drives are connected back to our control panel with DC power on the orange lines and Ethernet data on the black lines. So if you count up all the cables in just this aspect of your system, you got 16 cables that you've got to purchase, install, manage, and deal with. So what happens if we change everything to PoE and integrated motors? So we get rid of the power supply in the control panel, we go to an Ethernet switch that has PoE plus ports on it, and we swap out all the axes with integrated motors. Now we're down to just 4 cables. So we go from 16 cables down to 4 with no reduction in functionality or performance. That's a pretty significant difference. Now I'd like to talk about a few benefits of step servo, so our closed loop stepper technology. So this slide shows the speed torque curve of this TSM14 integrated motor. The dark blue line shows the torque versus speed that you would get from the motor alone, not taking into account closed loop control. So if you ran it open loop, for example. The light blue line is what we get when we run it as closed loop servo, which is we get a peak torque range. Now, it may not seem like that much in this chart, but it makes a big difference when it's in the machine. Compared to a conventional step motor, a step servo motor will be able to accelerate and decelerate significantly faster, especially in indexing moves or point-to-point moves, and this can increase your throughput. It basically shortens the move time, shortens the cycle time, and you can get more cycles per minute with a step servo motor. And in this particular example, we get that peak torque up to almost 600 RPM. I mean, this speed torque curve shows the motor going out to 3,000 RPM. Sure, it has a little torque out there, but most stepper applications are under 1,500 RPM. Another benefit is because we're controlling the step motor closed loop, it means that the current in the step motor is directly proportional to the torque demand. Unlike an open loop step motor where we're pushing full current all the time into the motor, the closed loop motor only draws the current that it needs. So what happens there is we end up with a much cooler operating motor. The photograph in this slide is taken from a test of two identical step motors. The one on the left is run open loop in the traditional step motor fashion. The one on the right is run as step servo closed loop. You can see after 30 minutes of operation, they're both doing the exact same work, and they reach thermal equilibrium, and the motor on the left, the motor temperature is about 76 degrees C. The step servo closed loop motor on the right is less than half of that temperature. And that is directly a result of only putting the power into the motor that we need to. So we're not wasting power in heat. It makes a higher efficiency motor. And of course, the motor runs cooler as a result. And then the third benefit that a lot of users appreciate is that step servo motors are much quieter. And this has also a direct result of only putting the current in the motor that it needs, as opposed to full current, full open loop current all the time. This chart shows audible noise as measured with a precision microphone in decibels versus speed. The orange line is the open loop motor. The blue line is the step servo closed loop motor. And you can see over a wide range from about 0 to 17 or 1800 RPM, the blue line, the step servo closed loop line, is much lower. And if you pick a spot on here, say 600 RPM, the step servo motor is more than 10 decibels quieter than the open loop motor. That's a lot. If you're standing next to these two motors and they're running at that speed, it's night and day, the difference in audible noise. Now, a lot of applications don't care about that. They can be noisy as you want, but there are some applications where noise from the motor is a big concern. And so step servo plays a big role in those applications. Next, we talk a little bit about some of the additional features of the TSM14 PoE. So it's an Ethernet device, so communication is, of course, very important. We support a couple of popular industrial network protocols. The first one is Ethernet IP. We support communications over Ethernet IP with Rockwell controllers, with Omron controllers, with basically any Ethernet IP controller that you might use. We also offer add-on instructions for RS Logix 5000. So if you have a Rockwell PLC and you want to incorporate one of these devices into, say, a Compact Logix or Control Logix project, it's very easy to do with those add-on instructions. We also support Modbus, which covers pretty much every other PLC out there and a lot of HMIs as well. And then we offer our own proprietary command language called serial command language, or SCL. This is a simple text-based command language that you can use from just about any controller. We have a lot of our users who are programming their own code on a computer or PC will use SCL. A lot of users who are using LabVIEW will use SCL. So pretty much whatever controller platform you're using will have you covered one way or another. In addition to getting commanded over the network, the TSM14 PoEs have onboard motion control. And what that means is you can store a motion profile, accel, decel, velocity, distance, or position parameters, all in different profiles or complete programs of various profiles. We can store those in non-volatile memory on the motor. And those profiles are created with QProgrammer, our software, which is based on the same command set as SCL. So it's a simple text-based language, but it's quite powerful. You can run those profiles or programs at power up of the motor, so it can run on its own when it powers up, or you can trigger those profiles over the Ethernet network, whatever works best to your needs. And you can mix in both modes if you want, and it makes it very flexible for you if you want to offload some of the motion profiles from your own code in your controller or your PLC onto the motor, or if you prefer to have that all in the PLC or your own code. And of course, it supports all the primary move types, incremental or indexing moves, absolute or positioning moves. It can home to a reference point at the startup of a machine. And then, of course, it does velocity control moves and jogging moves as well. Now, if you need a little more torque out of this NEMA 14 motor, we offer planetary gearheads. They come pre-assembled onto the motor. Standard ratios are basically from 4:1 to 32:1, and there's some other ratios available if you need it. Okay, this next slide shows a couple of things. One, it's kind of echo back to what I showed a few minutes ago. It's got our same basic connection block diagram. Here, it's important to note everything in this network is PoE plus, so it's at 25.5 watts of power. So we've got our Ethernet switch over on the left. It's providing a data-only connection to an HMI, and it's providing power PoE plus connections to our 3 integrated motors. And then the HMI is actually communicating to the 3 motors over Modbus. The second reason I want to show this is what I'm going to play next is a short video. It's a video of a demo that is exactly this setup that you see on the slide here. It's a video that we took at a trade show in the fall where we introduced this product. I'm going to play it muted because the audio quality is not great, and it's only about 28 seconds long. So in the video, you'll see our product manager, Mike. He's going to be pointing at the demo, and I'll voice over a couple of things while we're watching it. So here we go. So as the camera pans down, you'll see on the back of the demo, there's our switch on the left and the HMI. And then the 3 integrated motors on the base of the demo. The middle one has a gearbox. That's why it's moving so slowly. And then Mike disconnects the Ethernet cable from the first motor. It powers down. And when he plugs it back in, the motor powers up, establishes communications with the HMI, and starts running again. That was kind of quick. I'm just going to play that one more time so you can see it. Here we go. So when he plugs it back in, if it doesn't occur to you immediately, he's hot plugging the motor. So he's not turning the Ethernet switch off first to plug the motor in. And this is, again, another very user-friendly, easy to use thing about PoE is you can hot plug the motors with the Ethernet cables. Okay, a little bit about application examples. So this is a NEMA 14 frame step motor. It's closed loop, so it's like a better version of any NEMA 14 frame step motor that's being used right now. It's got more torque, it runs quieter, it's cooler. It can produce more throughput, but all the same applications still apply. So any linear actuator applications, direct driving a ball screw or a lead screw, any rotary applications for direct driving small rotary actuators or timing belts and pulleys, those are all fair game for this product. In addition to that, since we launched this product late in the fall last year, these are some of the industries that have started to adopt the technology. Laboratory automation, I won't go through all of these, but I'll just give a few examples. Laboratory automation has a lot of small step motors on that equipment already, and Ethernet is ubiquitous in the controls in that environment. And for example, fluid handling equipment uses a lot of step motors. So there are a lot of applications for adjusting, turning, picking product in that equipment. Peristaltic pumps is kind of an interesting one because peristaltic pumps, especially smaller ones, are often driven by step motors, and it works out great. And in most applications, the fact that the open loop step motor runs hot is not an issue. But in some applications, the heat from the step motor actually causes problems because it heats up the media in the tubing that's running through the pump, and that can mess up processes downstream from the pump. So in those applications where temperature control is critical, rather than putting a chiller on the tubing or doing some other type of temperature control later downstream, just put a closed loop stepper on there, put a step servo motor on there, and the temperature issues go away. Building automation is an interesting one. If you stayed at a high-end hotel recently, well, not super recently, but maybe last year, you might have noticed that there's a lot of automation going on, particularly in high-end hotels, where you may enter the room and suddenly the shades go up and the curtains open and the lights turn on. Well, there's automation there, and PoE is very advantageous in those applications because it doesn't require an electrician to run 110 volts, for example, up into the window to power a conventional motor. All you have to run is an Ethernet cable up there. And now it's low voltage. You don't need a trained personnel to do it. It makes it significantly easier to retrofit older hotels, for example. Material handling, gate controls, lever controls, robotics, end effectors, electric grippers, things like that. There are quite a few. 3D printers is a popular place for step motors. Electronics assembly, any place you're inserting, clamping, rotating, orienting, things like that. And then, of course, security cameras, pan, tilt, zoom. These are some of the industries that are adopting this technology already. Okay, a note about compatible hardware. So I hope I made the distinction clear enough in this presentation between plain old vanilla PoE and PoE Plus, Type 1 and Type 2. To get the full power out of our motors, you need to have a PoE Plus switch. Fortunately, pretty much every industrial switch manufacturer out there offers PoE Plus rated ports on some portion of their product line. So this short list here, there's no bias towards any of these. It's just alphabetical listing of a handful of name brand switch manufacturers that I was able to quickly find who offer PoE Plus ports on their switches and injector products. And that includes both switches that have RJ45 ports as well as M12. You can see a couple of pictures in here are M12 connectors for switches that you might want to house outside the control panel. And then the last slide of the presentation I've reserved for looking ahead. So what we've talked about up to now is 25.5 watts, what we can do with that in terms of motion control. And it turns out we can do quite a bit in that NEMA 14 frame size and that integrated motor. But where do we want to go from here? And the obvious answer is more power. We want to get up to Type 4 and take advantage of that 71 watts. And maybe even more as the specification grows and companies are able to develop higher powered standards. but more power equals larger motors. So we're at NEMA 14 frame now. 71 watts will take us well into the NEMA 17 and 23 frame sizes and allow us to do even more applications with nothing but an Ethernet cable. So that's it for my presentation, short and sweet. Thank you for attending. If you want more information on this product, you can head to appliedmotion.com/PoE. And we have plenty of time for questions. So, Bob, I will turn it back over to you.
Thanks very much, and great presentation, a lot of great information. We've got a lot of great questions lined up, so we're going to get into those in just a second. If you'd still like to submit a question, type them into the question window on the side of your screen and hit the submit button. And while we're answering those questions, please complete the feedback form, which is located at the bottom of your screen. As I said, we've got a lot of really good questions that have come in here already. We'll start with this Jeff Rutner from Command. Can multiple motors be electronically geared to a master motor?
That's a good question. So any gearing between motors in this kind of scenario would have to be done over the Ethernet network because these motors have no I/O. At some point, we may develop a solution that has I/O, but this device is just an Ethernet connection, and currently the protocols we support don't offer that kind of speed. So we would have to go to a more advanced real-time Ethernet connection to do that. And at the moment, we don't have that solution. So no, I would say for electronic gearing to a master motor, this is not the right solution at this time.
Very good. James Endres from RE2 Robotics. This is a good question. How do you prevent noise in the servo power from impacting the quality of the Ethernet signal?
That is a good question. I would have to lean on, I'm sorry, I would have to defer to some of our design engineers. Noise is always a problem with switching amplifiers and with motor drives in particular, but we have no problems with that now. So I don't know if we've done additional shielding inside the drive to protect that, or if simply the twisted pair and noise cancellation or noise control circuitry in the typical Ethernet port is sufficient by itself. I'm sorry, I can't exactly answer that, but I can tell you that we don't have problems with that.
Very good. John Tashigan from ConAgra Brands wants to know, how big of a torque do these TSM motors get?
So this is a NEMA 14 frame motor, and from the, I can pull the speed torque curve back up. They produce about, hopefully you can see that, they produce about, between 15 to 30 ounce inches in the lower speed range. So it's not a ton of torque in terms of the overall spectrum of motion control motors on the market. It's on the smaller end of step motors right now. But we can increase that torque quite a bit by putting a planetary gearbox on there if the speed is slow enough.
Great, thank you. Mark Urbentinger from Industrial Control, is there an auto-tune option for the step servos?
Not at this time, no. There's okay. Like a traditional servo, when you go into the tuning software, we guide you through it. You select base tuning parameters for the motor, and in this case, the tuning parameters are kind of baked in because the motor and the drive know each other, so to speak, because they're integrated. And you set in a load inertia, and then the default parameters for tuning are set for you. But it's not what I would call a traditional auto-tuning function.
Very good. A couple questions from Evan Reed at NAMPRO. First, is the PD specification per port or for the whole switch?
Yeah, so is the PD specification per port? So when you're looking at an Ethernet switch, I think the question is, how much when a switch rates, how much power is available. what does that mean exactly? So the thing that I've seen most common amongst switch manufacturers is they give a power, what's called a power budget. So each individual port, let's say you have a 4-port switch, and each port is rated to provide up to 30 watts. So that would qualify for PoE plus. So if you had 4 ports at 30 watts each, that would be 120 watts. But the power budget on that switch might only be 100 watts. So what that means is that you might only be able to use 3 of those PoE plus ports at any given moment for our motors. Or if the motors aren't running all the time, you know, your power demand is going to be less. So you could potentially run 4 motors at the same time as long as some of them are resting while others are moving, so that you stay under that 120 watts. So the answer to that is, generally speaking, what I've seen is the energy budget. So you'll have to play with the numbers to make sure that the number of motors you want to use fits within that budget. And I'm sorry, I want to correct one thing I said. I said 120 watts. It's actually 25.5 watts at the device. So you'd only be 102 watts. So a 100-watt budget would probably be just fine. But anyway, hopefully that answers the question.
Yeah. And also, Evan asks, does Mode B allow more power to be carried over the Cat 5/6 cable?
Not that I know of. My understanding is that the amount of current present in an Ethernet data signal is so low that the fact that we're running power over it, you know, the power that we're running consumes the majority of the current carrying capabilities of the wire. So my understanding is no, you don't get any more power over Mode B. I'm not 100% on that.
Okay. We've talked about the power going through the cable itself. The questions come in, how long can the Ethernet cable be?
So best of my knowledge, it's 100 meters is the longest you can go with Ethernet and still guarantee that that 25.5 watts at the device. And I think that number is based on Cat 6 cable.
Okay. Very good. And how fast can the motor run?
So step motors are an interesting little animal in that their torque drops as speed increases. So the answer to that question is always, how much torque do you need at what speed? If you don't need a ton of torque, you know, that's where you have to look at the speed torque curves. If the torque you need out at full speed falls within the curve, you can run 2,000, 2,500, even 3,000 RPM. But if you need all the torque that's available down in the low end of the torque curve, obviously you don't have that at the high speed. So anybody who's new to step motors, I always say you have to look at the speed torque curves. Whatever torque numbers you see in a table are just there for reference in comparing like apples to apples between different step motors. You always want to look at the speed torque curve.
Very good. And this is more of a practical question from Jonathan Gamble at Untitled Technologies. What happens if you exceed the power specification? Do you get a brownout condition, or is the power turned off?
So the motor, so let's see, how could that happen? So the switch is going to only allow so much power to the motor itself. And then the motor, the drive is only going to put so much current into the motor based on its own power capabilities. So what would happen is the only way that the motor would try and draw more current over the Ethernet cable than allowed is if the motor tried to produce more torque than it was really capable of. And that's not going to happen. The motor drive is going to limit how much torque is available. So basically, like any motor, if you try to move a load that it can't move, you'll get a position fault. So if you connect a little motor to a really big load and you try and turn it, it's just going to fault. It's going to say, I can't move that. But it won't go to a brownout.
Okay. And is there a duty cycle limit?
No, not on this motor. It can run full torque all day long.
And what field buses does the motor support?
So right now we support Ethernet IP, Modbus, and well, those are the two field buses that we support: Ethernet IP and Modbus.
Very good. And I think we got time for one more question here. Where do you buy a Power over Ethernet injector?
So I would say first off, start if you're using Ethernet networks now, and you're using industrial switches or any type of switch now. I would say start with your current vendor and see if they have any options. But the compatible hardware slide that I showed earlier, which I'll pull back up now, this was I literally spent maybe 20 minutes online looking for PoE plus industrial switches. And of these names up here, I know Phoenix Contact actually makes a line of DIN rail mount injectors in addition to their switches. If anybody from any of these companies on the line, I apologize if I don't know your product line well enough. I'm sure some of these other companies make injectors as well, but it's really easy to find them. You just want to make sure you're looking for PoE plus or Type 2 802.3 AT, and then that'll give you what you need.
Very good. Well, that's about all the time we have for questions right now. If we didn't get to your question, we'll be in contact with you soon to answer those questions offline. So I want to thank, first of all, Eric Rice for a great presentation, a lot of great information out to our audience. And on behalf of Machine Design, I'd like to thank Applied Motion Products for sponsoring today's event. Thanks to everyone for joining us. That'll conclude today's presentation, so have a great rest of your day and stay safe out there.